we are here today for introduce to you how we use Flink in Intesa Sanpaolo. I am Rozarta, I'm a software engineer in Intesa Sanpaolo, and he is my colleague, Andrea Fonti, is a big data architect on Agile Lab. I work in a team called Code Garden. It's a team of developers who focus primarily on implementing and maintaining the copy banking infrastructure. Copy banking is a process that replicates the data in the master database in near real time to internal target database. And we also work on open banking projects that are some projects focusing on data ingestion from external provider for use the data inside the bank. For the copy banking, we use the change data capture. That is a method used to identify and track changes in a database in real time, like when you have an update or delete or new data. And we do this without having to perform full data refresh. These are the key features of the CDC. So we have the real-time data capture, data synchronization between different databases, efficiency because we don't have to make batch processes or full table scans, and scalability. These are the common uses of CDC, but we will focus on mainframe offloading because it's our use case. And the mainframe offloading with change data capture enables real-time replication mainframe data to modern platform. And with this, we have some read replicas that help us to reduce the cost of MIPS consumption. And in this read replica, we can have different data model like documental, key value, relational, but writing is still through the mainframe. This is the pipeline architecture of of the copy banking. As you can see, there is a mainframe database. Near is the Oracle Golden Gate CDC, where we extract the information of the action that happens in the mainframe and send it to a Kafka topic. This Kafka topic is written by a Flink job that will transform the data and write it inside a database, Postgres, Oracle, Mongo, or a topic Kafka. The requirements of this pipeline are that data must not be lost. We need that this replication pipeline is in near real time with a minimal latency. The order must be preserved as it happened in the source database, and the pipeline must be idempotent because we don't need to have duplication of data. We have to maintain consistency. Okay. This is an example of a message that is sent to the topic Kafka by the CDC. I'm sorry. We have the table where the action was performed. We have information about how the data changed, like how it was before and after, and some information, some metadata information about the transaction. For doing that, we need to change AR model to documental model, and this is an example of how it's done even with tables that have like foreign key. And this is how we build the pipeline. First of all, we think about the architecture, so how the replica topology is, the traffic characterization, the output data model, in what kind of database replica we need to write the data. Then we develop the job, we test it. Sorry. Then we deploy with the change management, and once he's deploying inside with the Flink UI and the Rozarta platform, we monitor it. We see the logging, the checkpoint, and there are also the system of alerting if something is not going as it should, or the minimal latency is not verified. Here are some examples of some architecture. This is a simple architecture when we read from Kafka and we write the data inside the replica destination. Here's a stateful job. When we read from two different sources on Kafka, then we save in the state of Flink some information that may be useful, and then we write it in the database. This is an architecture with the timestamp column. This is not stateful. We use the database as a state, and we, for doing updates, we use a merge when we check the timestamp for updating the data. This is an architecture with the failure domain isolated. As you can see, we read the data from different sources with some job links. Then we send it to topic Kafka. They are written from another job link that writes it to the DB. And this is helpful because if one of the first job fails, it doesn't affect all the other, and so the other job can continue writing data. Now we talk about the development part. For writing job Flink in Intesa, we have developed a framework called Scrat. The goal of this framework was to standardize and simplify the development of Flink-based application and to integrate it with the enterprise architecture with the components supporting streaming and change management. The benefits are that we use a declarative logic design. So every part of the job Flink, sync, source, logic, you can write it in a declarative approach. So we have an abstraction of complexity because it's easier. There is the introspection because every part of the Flink application can be seen as a data, and you can inspect it, configure it, and validate it. And obviously the integration with the bank enterprise architecture. Here there is an example of an application written in Scrat. We have the description and the name of the application, the modules that the application will need to use in the logic, and then the definition of a flow with his source, sync, and logic that are defined with the factory. And now I will pass the stage to my colleague that will explain you the life cycle of Scrat and components.
Thank you, Rosie. Hi, everyone. Thanks for having us here. It's a pleasure meeting the community here at Flink Forward. I helped Intesa Sanpaolo in building this framework. I'm from Agile Lab. We are a big data consulting firm. And I'll go a bit deeper in why we built an application structure like this. Since having this kind of structure, they have like thousands of jobs. These jobs cannot just be developed and every job be different one from the other. So we try to give these jobs a structure so that when we debug something, we do the problem determination, there is a common structure between the applications. So we chose an approach where that application definition will be built into 3 phases. You define the application, so you have a declarative approach where you mix and match Legos. Each one of these components informs the framework of needed configuration keys, which are the data types, etc., etc. You can reuse components. So if you have a reusable logic like field normalizing or mapping of data types, you can just put that logic in multiple flows, and the framework will take care of wiring that logic with different configuration coming from different places. During the definition, external dependencies and dependencies are involved. So for example, you don't need to bootstrap Kafka or other data sources just to run the definition stage. And after you run the definition stage, you will get a data model that you can inspect. I come from a functional programming background, so for me everything is an interpreter or a compiler. So here we are interpreting the definition and we can extract information and no imperative code code gets run here. So we can ask the application, can you render your high-level topology? We are not talking about a Flink execution plan. We are talking about a business-related topology. We are reading from this source, applying this kind of logic, and then writing to this destination in business terms. We can ask the application for, can you tell us which are the configuration needed and which is the configuration schema? The type safety is enforced, and the components can be safely reused. Then we move to the compilation stage. In the compilation stage, other wiring happens. So we call modules stuff that is cross-cutting. So for example, you can have multiple logics, and all these logics needs to do JSON processing. So it's a way of doing dependency injection without resorting to Spring or to IOC containers. We can swap modules, so we can mock stuff out. You will see that later. This phase is still lazy, but now we are loading real configurations. So we are not only telling the framework, these are the configurations we need. Here we are loading configuration and actually going ahead in the configuration step. And now we can ask the application for more details. Okay, now I know from which topic you are reading. Now I know to which topic you are writing. So you can implement maybe lineage, data flow on that. Here the application did not boot on Flink yet. Then we move to the executable phase. In the executable phase, the compiled topology will get compile down again, sorry for the repetition, to a Flink topology. Once we have a Flink topology, we have a Flink plan. Once we have a Flink plan, we can validate the Flink plan again. What I mean about validating it, there's a production checklist in the Flink documentation. Please assign UIDs to operate or do these checks. Also in the bank, they have requirements of ordering, strict ordering semantics. So here we are inspecting the plan to check if all the operators have UIDs. We are inspecting the plan to forbid shuffles that do not preserve ordering. For example, a rebalance in a Flink topology will not preserve order of messages. A key by should if the structure of the key is okay. A forward shuffle, so no shuffle is always safe. The developer can disable this if select a mode where ordering is not guaranteed. And also here, we can run these topologies on mini cluster. We expose test kits, and those test kits wrap the mini clusters that are available. So here is a class diagram. Let's skip this. The same stuff I already talked about. And this is, for example, an example rendering of that data model. Here we are reading from Kafka from this topic. We are applying this logic. We are writing to this Postgres location. The next step for this will be putting this data model in a microservice that is handling governance at the bank level so that we can, from the CI/CD, just publish this information about each job in a central location and have a global rendering of whatever is happening. You see also configurations. Then we built some Maven archetypes, since a lot of these jobs are quite standard. We have a simple archetype, an advanced one, and a replica archetype that is mostly configuration-driven. Just render that, and you have a kind of microservice in the streaming land that will do replica. So just configure your archetype and generate your application. Then there is an integration with the enterprise architecture of the bank. They need to do mainframe offloading. Doing mainframe offloading means reading from read replicas. What happens if the latency is more than 5 minutes? Maybe we should read from the mainframe. So there is a tracing infrastructure, tracing as in distributed tracing, and a failure bus module that is a topic where you can signal fatal failures and just switch the replicas from the read replicas, the microservices from the read replica to the mainframe. And then, since this is all standardized and integrated, so all the sources and things in Flink will get wrapped and get this behavior for free. There is also an event bus ingestion framework that lets you build application that needs to monitor this infrastructure. So there is also a standard way of building microservice that will monitor the streaming pipelines and switch what we call semaphores to read from mainframe instead of the read replica. So all the data that flows inside this framework has an analogy with network protocols. So we are reading from a Kafka source, and we get an envelope. So there's framing, an envelope with Kafka metadata, and then a payload inside. Do you want to extract a CDC-related behavior? Then just wrap your source with a CDC source, and you will get an envelope of envelopes. Do you need tracing? Just wrap your source in a tracing source, and you will get envelopes of envelopes. And this is how we propagate metadata along the pipeline without the developer actually caring about propagating metadata. They just need to transform and process the inner payload. OK. So then we focused on message deserialization. It would be wonderful if we could ask an application declaratively. The application declares how the data format looks like, and then we can ask that application for which kind of format are you expecting. So we have a message format descriptor definition that we can query is data right now. And this explains to the serialization framework how to deserialize metadata, how to serialize metadata, the payloads, integration with schema registries, with Avro, with JSON, and also how to extract the event time from the messages on Kafka. We have a lot of modules. Why we need modules? Because if you use standard modules, you'll get observability for free. So the REST module gives you the cross-cutting concern of making REST calls, but it embeds retry behavior, a lot of monitoring, observability, how much latency do you have in a call. So if we start from a monitoring dashboard, something is not working, a job is not checkpointing, maybe it's blocked. Then we look at standard metrics, and maybe there's a REST call that got stuck in a retry loop. So everything is integrated in the ecosystem of the bank. Then for replicas, we chose to use JSON as a lingua franca. So the payloads are serializable JSON nodes that are mostly strings that get converted back to JSON. And then we use a domain-specific language for JSON transformations. We don't like SQL for heavily nested structures. So there's a module that lets you compile JSON transform specification into a JSON transformer. So you just configure your JSON transformation. And there are multiple implementations of this module, since we can use JSLT as a transformation language, or Jolt. We can use Jolt since Jolt is integrated into NiFi, and so we can migrate NiFi workloads by just reusing the Jolt specs that are already used on NiFi. But for new use cases, we prefer JSLT since it's more powerful. This is how JSLT transformation looks like. Here we are joining two tables and doing some sums or length of our inner array. So we have n sidekicks for each superhero. And the JSLT structure closely mimics the document that will get written on MongoDB or on another documental database. Quite flexible, we like it. And then we developed the custom sinks. We have custom sinks for MongoDB, also JDBC sinks that do the duplication and batching. So if you're going to upsert the same row, those rows will be deduplicated in memory and just sent one time to the DB. And also we have JSON aware as JSON format, we call those. And the sinks that are JSON aware, they will use the JDBC metadata facility, or maybe other metadata facility for other kind of data stores, to try to automatically map the JSON structure to the database structure. So here you see kind of a configuration. So you need to upsert data in the user table. The key is the name of the user, and then you have 3 values. If you just inspect this statement, you don't get as much metadata as you need. So we can use a metadata SQL statement select name, number, color from user, that will just get prepared and queried for metadata, but never actually executed. And that is like a template that we use to derive information that the DB is not able to provide. For example, Oracle is not able to provide metadata for that merge statement unless you use casts into the values clause, but that is a detail for another presentation. So if the JSON does not mimic the structure of the table, you can use JSON pointers to point the sink to nested fields, and also you can override the data types, you can override the time zone for timestamp handling. So everything that comes wrong from the metadata of the database, you can override that manually. So having a DSL for JSON transformation, having a JSON-aware sink means that replica use case is mostly configuration in the simple cases, but you can also write stuff programmatically. Then we have to deploy these jobs, not by hand, since those jobs are 1,000. So we have application repositories. Application repositories contains the code and also the configurations of the application. Those get built by Jenkins. Jenkins will also commit configuration into an infrastructure repositories where other configuration lives that are more related to the infrastructure and not to concern of the development team. Then Argo CD gets triggered. It will sync the deployment with Ververica platform. The Flink job will start on OpenShift, on the OpenShift cluster, and start streaming data. Then we have a good monitoring stack that employs Prometheus for metric collection, Grafana and Splunk for aggregating logs and metrics. Performance. So when we talk about performance and you have latency requirements, each time you add a transformation to the same job, you have to ask yourself, will we have the same latency or will it be worse? So there's a matter of non-regression. There's also the matter of characterizing the job for the first time. How can we do that? We implemented the concept of scenario. So we can load data and there is an application that we will use that data. So scenarios can be functional, scenarios can be performance testing. But we have the concept of generators. So generators are deterministic. When, before doing a job, we characterize the traffic that we are receiving from Kafka. We are doing data quality, passive data quality, so understanding the statistical characteristics of fields. Is a field an enum? Is a field a string? How it is distributed? Is an integer? How it is distributed? And this stuff. So generators are deterministic. Same generator, same seed, same data generated on Kafka. And then we use distributions from Apache Commons Math to sample maybe normal distribution or other kind of distribution and generate realistic data that is random, or we will need to do anonymization, use actual production traffic, and that is a pain in the banking sector. And then after we have that, we will pump a lot of messages on Kafka and start a job from earliest. So it's like traffic was already there. So it's like you have infinite velocity when data is coming to your job, and that is the max throughput you are going to reach. Or you can use this generators and load these generators on a microservice as a jar. That microservice will load that jar and run the traffic generation online on Kafka on a performance testing environment. And then you can see if your job actually tracks the envelope of the traffic or it lags behind. Then we collect metrics, lot of metrics. And then we change parameters and see how stuff goes. Then we record these parameters in a performance report. And next time we do a change to a job, we can just compare. Are we worse? Are we better? Should we change configurations? Should we change parallelism? So there's more science here than feeling, let me say. And then you need to do operations. So you have to maintain these jobs in production. You need logging. There's a module in the framework for structured logging, and logging gets ingested into Splunk, and you can query logs from Splunk. You have a lot of standard metrics in the framework. You can define also functional metrics or application-driven metrics, and those get automatically monitored. There are standard dashboards for all the metrics that are exposed by the framework, and the application team can do custom dashboards if they want. And everything, this is everything. Thank you. Any question? Don't be shy, please. Okay, so if there is no question, maybe I was not clear. Sorry, it's me in that case. Anyway, thank you for having us, and thank you for letting us be here. It was a pleasure meeting the Flink community. Thank you.